Welcome to my talk, More Productive Actuarial Modeling with Julia and Julia Actuary. An alternate title might be Why I've Started Using Julia for Many of My Actuarial Needs and Why You Should Too. First, please take a moment to read the disclaimer and antitrust guidelines, and thanks to the sponsors for this conference. Today's talk, there's essentially three sections of core content. First, I want to introduce myself though. Second, I'll talk about what is Julia and why is it so powerful. Next, I'll talk about actuarial packages that are already available in Julia and conclude with thoughts as an open source actuarial developer that's been doing this for several years now. So first, with my work experience, I've worked in a wide range of actuarial functions from pricing to modeling to planning and capital management to reinsurance and deals in M&A. I've worked at several companies including Manulife, Resolution Life, Couvert, and Fortitude Re. Technically, my background is very diverse. I first got into actuarial modeling when I was my first role at John Hancock, when I used GGY Axis, and I thought, if this is the leading edge of actuarial modeling solutions, I should be able to do better than that. And that was my motivation for getting into programming. So for commercially available software over my career, I've used extensively Axis, Alpha, to a lesser extent Bondage, Slope, and of course Excel. I have been programming over a similar amount of time. First in VBA in order to automate tools associated with processing and testing Axis output. Then, having become amazed at how much more productive I was knowing VBA over basic spreadsheet capabilities, I decided I should teach myself how to program from the ground up and picked up a book on C. I worked through that book over a couple of months and decided that I felt like I had got enough of the basics and I should move on to a higher level language and picked up R. I used R for several years, doing things as early as trying to predict the output of cash flow testing results across different scenarios using machine learning back in around 2013, predating the use of a lot of similar models that I've picked up over more recent years. However, I found R to be quite an awkward language for doing general purpose programming, and instead decided to switch to Python, which back in around, say, 2015 or so was very much not as popular as it is today, as weird as that sounds, but was kind of pitched as a general purpose language that could do statistics. At the time, Pandas was the leading data frame library. There was NumPy and SciPy. But spent several years programming primarily in Python. Then around 2017, 2018, started dabbling in Julia and have quickly switched most of my programming to using Julia. And that's a lot of why that is what this talk is about. Along the way, I've also dabbled in a number of other languages, learning enough to feel like I got a grasp of some of the concepts and features, syntax, like paradigms of programming in those other languages. Some of the more in-depth ones include Go, Scheme, Haskell, a little bit of Java, Dart, a little bit more JavaScript, a decent amount of Mathematica, but that was always when doing more of the math-heavy work, and then some MATLAB from back in college days. I am also the author of Julia Actuary Packages, which collectively is one of the most popular set of actuarial packages on all of GitHub. Announcing publicly for the first time, plan to publish a book with my co-author Lee Yoon Tien titled Computational Thinking for Actuaries and Financial Professionals sometime in 2025, and we anticipate a public beta for the open access book to be coming soon. Follow juliaactuary.org for updates on that. So Julia, what is it? It's a programming language, and the reason you should learn about it is because it's fast, it's productive, and it's fun. So one of the first things that people like to talk about is how fast Julia is. That's actually going to be a very small portion of what I want to talk about today, because I think we can take for granted that it is a fast language. I do want to do a couple of comparisons first so that we kind of level set how it actually benchmarks against other comparable languages. But the majority of what I want to talk about is some of the aspects that make Julia a very productive language, where you have a problem in front of you and it is able to accomplish, help you accomplish building the solution to that problem more rapidly, because of the concepts, because of the tools of the language that other languages do not provide. So the first benchmark, this is called the life modeling problem. This was actually proposed on a actuarial, I think actuarial open source group on LinkedIn. Somebody had written an implementation of a net premium calculation, and posed a challenge to the members of that group and said, here's a problem that is typical of life insurance modeling, where you need to do an iterative calculation and then transform the results of that iterative calculation to determine something like a net premium. Various people proposed different solutions in different languages, different approaches, and this is the result of that. On the left side of the plot is how long it took to calculate the net premium for a given policy. So it is log scale, so it ranges from 10 nanoseconds at the second from the top where Julia is, all the way up to 1 million nanoseconds, which is how long the data table approach in R took. So it's pretty clear from this that there is a wide range of run times for this problem. And fast languages like Julia and Rust are able to accomplish the calculation as fast as the computer's hardware will allow. Conversely, languages like Python and R, and even like JIT compiled Python like Numba, do not perform nearly as well. The description of the distance is how long light travels during that time frame. So over the period of 10 nanoseconds, light will travel about the height of a basketball hoop. Over the span of 1 million nanoseconds, light will travel all the way to the altitude of the International Space Station. So you can tell that there's a very wide range of outcomes. The two different colors of the dots, vectorize versus accumulator, are two different approaches to the problem. Vectorize uses arrays of numbers like NumPy. The accumulator uses an iterative approach, looping over the values instead. Another benchmark is looking at libraries that calculate in the internal rate of return on 60 years of monthly cash flows. NumPy has a financial sublibrary, which is probably the default library for many people working in Python. That IRR function takes over 100,000 times longer to calculate the IRR than does the IRR function from the Julia library. Python does have an alternate, less well-known library called Better, which implements in IRR solve using a Newton-based method, which is only 91 times slower than the Julia implementation. One last benchmark is the Black-Scholes option price, where the task is to simply calculate the value of a call or put option using the Black-Scholes option formula. Implementing this using the most straightforward way you'd implement this problem, using the math shown there, and calling functions like the cumulative normal distribution, so kind of testing pure math speed. Python is close to 20,000 times slower than Julia, and R is almost 100 times slower than the naive Julia implementation. Why does this happen? R and Python are high-level languages, in large part interpreted rather than compiled. Compiling allows the computer to implement machine code that is optimized for the given hardware, whereas interpreted languages generally have to run through multiple layers at runtime to calculate the solution. This leads to what some call the two-language problem. There's one language for productivity, such as Python, and another that is for performance, such as C++ or Fortran. Some languages don't have the semantics or the specification that allows them to be fast. So the work gets outsourced to the languages that can be fast, which is why you see libraries like NumPy or SciPy, which are predominantly not written in Python and are essentially wrapper libraries to a faster C++ or Fortran implementation. And there have been lots of attempts to make Python fast, from Numba to CPython. A recent popular promised attempt to make Python faster is Mojo, which is a new language which was described as being a superset of Python, where you could write, like, take old Python code and Mojo would run it and it would be fast. However, they've even recently given up trying to be a superset of Python and instead describe it as a way to extend Python, not in a way that's dissimilar to using C++ to make Python faster for data science and modeling purposes. And what is it about Python that is limiting like that? There's things like Python is interpreted. It doesn't have type specifications to allow the compiler to infer types throughout the program and compile it to fast machine code that does not require lookups. There's limitations related to multi-threading and using devices like GPUs from Python, which generally have to, again, use libraries like CUDA or other glue libraries. So, given that we can agree that Julia is fast, I won't go into the details of why that is, but I don't want to talk about that very much because I think it's something that's shiny, but it's, in the long run, not as useful, because a lot of times you can get performance by writing your performance critical code in a different language and simply calling it from Python or R. What I do want to talk about is what makes Julia so productive. And I'll lead with a few test cases from the real world. The New York Federal Reserve rewrote their macroeconomic forecasting model and saw, depending on the part of the code, somewhere between an order of magnitude and 2 orders of magnitude of speed up. They found that the amount of code that they had to write was reduced by about half, which means that there's less code surface to have to maintain, and that's a result of Julia being more expressive and having ways to implement problems in a way that is more concise and readable to the user. The large European insurer Aviva utilized Julia for Solvency II modeling and found it to be 76 times faster on a single computer versus an entire cluster running the IBM algo modeling solution. They did not specify how much shorter the code base was. They described it as much smaller than the algo commercial solution. One other actuarial/financial example is Conning, which implemented some of the stochastic risk scenario modeling. They found that their solution was 5 to 10 times faster, but didn't say what they were migrating the code base from, but described Julia as having simpler code with very high productivity. Why is Julia so productive as a language? I would describe it as that it's a high-level language that has very sensible defaults and a robust standard library, and it gets the basics right. An example of that is looking at how to draw random samples from different values. So there's 4 random samples that we do. A random uniform from 0 to 1, a random normal, a random Bernoulli outcome, and a random selection from a set of values. You see that with Julia, it's the same function for each of those. And Julia is able to use different methods which implement exactly what we want. We're drawing 100 different samples from those 4 samplers. With R has different function names depending on the distribution type or depending on what you're trying to sample, which is one of the things that I always found really difficult to remember at times. Constantly needing to look up in like the help manual or the vignettes about how to do certain things, because the function name would often be different despite nominally doing very similar things just on different objects. Python is kind of like R in that it's a bit scattershot, so there is no like built-in like random variable sampler, so people generally use that's not true. There is random number sampling, but not in like vectors that people actually use. So people tend to call like NumPy or SciPy. Again, here, I found this a little bit odd when putting together this example, but depending on the thing you're trying to sample, you're either going to use SciPy.stats or NumPy, and the way that you call it is not consistent. So you can see when you're calling SciPy stats, you end up using like SciPy stats.uniform.norm.Bernoulli, but then NumPy, you have to do NumPy.random. So there's less consistency in R and Python than in Julia. And a fun fact is that there's actually some research done with the large language models that have come out recently. And one of the explanations for why the large language models are able to produce better Julia code than R or Python is because it's theorized that Julia is just a more consistent, concise language than R or Python. This is another example which is a little bit technical, but serves to, I think, go into a little bit more depth about what makes Julia more powerful than some of the alternatives. So what this is it's termed the expression problem, where traditional object-oriented paradigms do not allow for the extension of both representation or data types and behavior, meaning methods. Generally, when you want to extend the representation or the behavior, modifying one can be easy, but then modifying the other can be very hard. So here's the setup. We're trying to model an insurance product, and we've got a couple of like subtypes. In Julia, it looks like this. We have an abstract type called insurance product. We have modeled 2 subtypes, term life and whole life. Each one of these has certain variables that are important to the product. Those variables are different, but we then are able to add a couple of functions, and these functions vary depending on whether it's term life or whole life. The full implementation is left as an exercise to the reader. 2 example functions are premium and reserve calculation. So what is the, say, net premium requirement, and what is the reserve at a given point in time? This is how you would define like basic data types and basic methods with Julia. With Python, generally the way you'd want to do this is implement an abstract base class. That abstract base class would have certain to be defined methods such as calculate premium or calculate reserves. And then specific data classes would implement those interfaces. So the data and the behavior are bundled together in this class, representing a term life insurance product. This only shows term life. You'd repeat the same thing for whole life, and we'd essentially have in about twice the space exactly what we defined over in Julia. Now, let's say that the product people come and say, hey, we actually want to implement a deferred annuity product, so we need to be able to model a deferred annuity product. In Julia, this is very straightforward. You'd simply add a new deferred annuity data type and implement the existing methods. And then if you need to add a new function, a cash value, which the other two products may not have or may not be important for our modeling, all we have to do is simply define a cash value function that operates on the deferred annuity for a given time. This is what's called multiple dispatch. This function, the behavior depends on the combination of the inputs. So here, the combination of a deferred annuity object and a time value dictates that Julia will select this method, not defined, but it would use the method defined here whenever cash value is called on that combination of arguments. That's contrasted with single dispatch, typical of object-oriented languages, where for a given class, the method will only depend on the first argument. So in this simple example, you don't necessarily see the full spectrum of the fact that in Julia you could have 5 or 6 combination of arguments, and every one of those arguments would contribute to which method you select. Whereas in Python, only the first argument matters. And so you end up with a common pattern in Python of if the argument is an array, do this. If the argument is a scalar, do that. If the argument is a special object, do something different. And so you have to define a case statement where at runtime the program has to figure out which is the appropriate code path to use. So returning to the example, to add a new object for deferred annuities in Python, we would define a new class, deferred annuity, which has similar data types as, say, whole life, but we have a new method that we want to implement, cash value. Cash value doesn't necessarily make sense for term, and so in order to add the deferred annuity, we have to go back and refactor our abstract base class to be able to distinguish between, say, a product that has no cash value development, like term, versus a product that does, like deferred annuity. And that's a violation of good practice of trying to make code changes be as local as possible and not needing to modify other parts of the code in order to extend it. There are workarounds for this, and there's a lot of patterns that have developed around object-oriented languages where you kind of have very abstract patterns such as the visitor pattern in order to implement kind of solutions to the single dispatch problem where you can't extend both behavior and representation without modifying a substantial portion of the upstream code. This ends up being really powerful in Julia because it means that you can extend behavior or data types that are not part of what you own. And so in Julia, you'll see a lot of times that there's cross-pollination of packages where you have one package that implements units, like physical units, like meters per second, things like that, and a plotting library. And the plotting library and the unit library are able to work together, and they don't know about each other in advance. Whereas what happens in other ecosystems, like data types from one sub-ecosystem are not compatible with data types of the other sub-ecosystem, where you end up having libraries that implement arrays, but those arrays are not just a generic array, they're a NumPy array, or they're a JAX array. So there's limited ability to extend the behavior or representation from other libraries, so you end up getting repetition and incompatibility across major parts of the ecosystem. So I talked about multiple dispatch, and there's ways to essentially replicate traditional object-oriented in a more flexible compositional way. But Julia is very multi-paradigm. You can write in a very imperative or procedural style, so think like Fortran type of code. You can write functional, so like Haskell or Lisp-like, or like really cool high-level libraries like transducers, which are super powerful and actually powers the financial one of the financial models that we'll go through later. Array programming is also fully supported, so if you're very familiar with like NumPy type coding or programming on GPUs or TPUs, Julia has first-class support for that type of approach. It's also homo-iconic, which means that it's able to inspect and modify its own code. You can interact with Julia code as if it's data and modify that data, which allows people to do really cool things like implement macros, which are kind of like magics in Jupyter notebooks with Python, but like language-wide and much more powerful. As mentioned already, you can have a very object-oriented style of coding, or implement things using trait-based. So, for example, Rust is a language that uses traits to define how programs work and how behaviors of data types flow through different methods. And you can combine all of these. So in one part of the code, if it's very natural to represent something as an array, you can do that inside of a giant imperative procedural loop, or you can use a transducer inside like a bigger function that is just like very object oriented. So that's one of my favorite things about Julia is different problems have different, in my view, most natural ways of representing them, and the multi-paradigm nature allows me to just, okay, I'm going to do this in a object-oriented way. I'm going to do this using traits, and it feels supernatural. The downside to that is it's been called the curse of Lisp. Lisp is a much older language, but similarly flexible. And the curse of Lisp is that because there's multiple ways to do something, it can be a little bit frustrating at times, or feel like you're spending more time figuring out what the best way to do something is rather than doing it the only way that the language allows you to. I think I totally get that, and there are times where I feel that way, but I also feel like I wouldn't necessarily want to be programming in a language where there was one right way to do it, and that one right way involves, for example, not writing loops, like is the common advice in Python and R. So moving on to like some concrete examples. This is an example of combining a library with like custom code to do something that just every time I see it, it blows my mind. And what we're doing here is we've defined a function, policy account value, policy AV, which takes an object where we've defined some of the parameters of the object, and it's looping over that the components of the policy and determining how the account value progresses through time, and then it returns at the end of that loop what the final account value is. So this is a very simple dummy example where we're only projecting this policy 6 years. And what this looks like is we provide the inputs, so a policy with an annual premium of 1,000, a face value of 100,000, and a crediting rate of 5%. Projecting this policy, we see that the ending account value would be $4,048. What we do next is what I find so cool. Using the Zygote library, which is a reverse mode automatic differentiation library, I'll unpack that in just a second, we're able to calculate the derivative of the account value with respect to each of these inputs: annual premium, face amount, and crediting rate. So what this is saying is that if we incremented the annual premium by 1 the ending account value would actually go up by close to 7, which makes sense because we're paying premium for 6 years. So we're getting a little bit of the accumulation of the credited rate. If the face amount went up by $1, the ending account value would decrease by 3 cents. And that's because there's more net amount at risk and the COIs are dragging down the ending account value. Lastly, the crediting rate, if the crediting rate were increased from 5% to 105%, because this is like representing a unit increase in the input, the ending account value would go up by nearly $11,000. Of course, that's not what wouldn't actually expect a crediting rate of 105%, but you can just scale this down to say what would be 100 basis points instead. It would be 100th of that. 100 basis points would be around 100th of 105%. So we'd be looking at an increase of about $110 from a 1-point increase in the crediting rate. But Zygote, I said, is a reverse mode automatic differentiation library. So automatic differentiation is a technique to tell the computer to take a derivative. And it's not doing finite differences where you do like plus some amount, minus some amount, and then that tangent represents the derivative. It's actually calculating the derivative. And it does that by transforming the code that you write and taking the derivative at a bunch of different substeps using the chain rule that we learned about in calculus. Reverse mode refers to simply one of the techniques to accomplish that. The other approach is forward mode, but that's out of scope for this presentation. Another example is using R and Python inside Julia. So Julia is able to call out to Python or R so that you're able to use existing libraries either as maybe the functionality doesn't exist in Julia, probably not, but maybe it's more fully formed in some Python library or R library, or maybe it's just that you're working on porting some code over to Julia and you want to prove out that, all right, what the Julia code is doing is the same thing as what the R or Python code is doing. And it's literally as simple as, like you in this example, using Python call and then using conda package if you want to install like dependencies from Python. And rcall is similar, where you just use rcall and be able to use and install dependency libraries. So this is a super powerful way to like leverage the full Python and R ecosystem within Julia. So you can see that, like for example, in this R example, we've created a vector of 10 random normal numbers, and then we use this one sample t-test library or t-test function that's built into base R to calculate a t-test on this sample of Julia values, and it automatically is putting in, like transforming the Julia data into like the R data types when it calls that function. So that was just kind of a taste of what makes Julia so productive and why it can be very powerful and expressive and really faster to a solution for a problem than any other tool or language that I've used. The third thing that I want to highlight about Julia is that it's fun to work with. So you might have heard of like dependency hell in other languages. The developer experience in Julia is top-notch. Comparable to, for example, Rust is probably the closest peer to Julia for the kind of overall developer experience. There's a full-featured environment where you can use like VS Code, a REPL or repo. There's like an integrated package manager which does both like dependency management and environment management, and that's like built into the language, so you don't have competing things like poetry or conda, which like are done differently. Now there's like UV, other things in Python. Dependency management and package management and environment management in Julia are like basically just works. It will download binary dependencies. As a really good example of that, using CUDA in Julia is literally as simple as adding, like you'd go into the package manager, just add CUDA, and the longest part of the install is just waiting for CUDA to download. That's all you have to do is add CUDA, and then you can do using CUDA, and you're working with GPU-based arrays. I have attempted installing CUDA many times in Python, and only a handful of times over the last decade or so have I got an environment that I felt like worked, and typically that was pretty fragile, and every time there were updates available, I would decline doing that because it took so long to get it set up in the first place. Part of that dependency management is that there's an ecosystem-wide use of semantic versioning. Semantic versioning is like the v1.2.7 type of versioning scheme. And it's system-wide, and it's enforced by the general registry. Of course, it's only as good as like the developers who set the version numbers appropriately. But it is taken very seriously across the ecosystem, and what it means is that you can pin packages at versions you want. You can update packages and have high degree of confidence that like it's not going to break your code. And it's enforced by the registry and used everywhere. Documentation and testing functionality is built in. So again, in other languages you have many competing implementations of documentation or testing. Julia just thought about that and said that's an integral part of having a modern developer and user-oriented language. Let's build it into the like language itself. There's a lot of different debugging tools, and the debugging tools are a little bit different than other languages because again, Julia is very dynamic. You can be interactively editing code, so sometimes you want a debugger that like does like literally like step line by line or step into the function, just like the good old like VBA debugger. Other times you're trying to debug like the statically compiled code, and so there's tools that kind of let you dive in and interactively explore not just like the Julia code, but also like what is it doing at like one step below, like after it parses that code? What is it doing in one step below when it does the like first compiler pass, like the LLVM code? Then like you can even get down to the machine code and look at like what are the instructions being issued to the CPU or to the GPU. And there's also versions that are integrated into VS Code, so you can run performance profiling or interactive debugging sessions, or explore like different layers of the call stack, things like that. Julia's a single install and you're up and running. So the recommendation is to go to julialang.org, install the Julia Up version manager, and from there you're able to install the latest release of Julia, install prior versions of Julia, and it's all kind of, again, that just works experience. Another thing is like it's a very smooth learning curve. So you can, part of the multi-paradigm aspect of Julia that I mentioned earlier, where you can write code in a very object-oriented way, in a very array-oriented way, you're able to write code in a way that's most familiar to you, and gradually shift to broader, maybe more flexible or more performant ways of writing the same, like solving the same problem. And the online community of people who are willing to support that is awesome in Julia. I've mentioned a couple times, but Julia does have really great VS Code integration if that's your preferred editor. I'd say that is the first class tool in Julia. Other things like Emacs and Vim have plugins, but they're all kind of based on the same underlying like code interpreter and parsing infrastructure. But from what I can tell, the VS Code is one of the best language integrations out there. Aside from the developer experience, there's just really cool stuff in Julia that you don't necessarily get with other languages. So Jupyter, of course, which for those who don't know, Jupyter refers to Julia, Python, and R. That's where the Ju, Pi and R part of Jupyter come from. So you get things like data science notebooks. You also get things like modern reimagining of notebooks called Pluto, which are, it's kind of like a Jupyter notebook, but there is no run all button because everything's connected. If you change a variable, other cells that depend on that variable will update automatically. The cool things, like I showed the Zygote library earlier, which has like language-wide automatic differentiation capability. So you can take an arbitrary set of code, not just like a mathematical type function, and you can get the differentiation of that. Like we saw that with the account value example, where we're differentiating through a loop that was iterating through policy steps. There's awesome data science libraries, from plotting to data frames to like file types and input output type of things. And my favorite visualization library of any language, Maki, or MAKIE, is really top notch. GPU programming is so much more accessible with Julia because you can essentially write the same code that you do for the CPU and just change it from being a like CPU array to being a GPU array. So it's kind of like the version of the NumPy, which you can do on GPU. You can just kind of transform your data into a GPU data, and it will run as you expect on the GPU. But again, so much more simpler to install the GPU dependencies with Julia than other languages. You get full Unicode support. So one of the things I find myself doing is, like, if I'm implementing a mathematical function, I'll sometimes use within that function that I'm writing like the same like Greek letters that are super common in the literature, and it helps the end user look at the code and be like, yes, it's not just like typing out like theta underscore bar. It's actually like a theta with a bar over it, and that ties to whatever like algorithm you're trying to implement. There's a huge scientific computing ecosystem, so everything from like high performance computing, like running on like giant supercomputers, to libraries that are like very focused on like extracting the last like drop of performance on a given set of hardware. There's like kind of scientific libraries if you're trying to do something related to like health or sciences. A lot of really interesting work going on. Lastly is like probabilistic programming. So this is one of my favorite things to dabble in, but probabilistic programming refers to essentially writing code that is designed to represent probabilistic processes. And Julia has libraries. One of my favorite is Turing.jl, where you're able to essentially define like this variable is represented by this probability distribution and run simulations or sample from that code. So a lot of cool toys. I haven't covered everything, but we need to move on to demonstrating some actuarial packages. So actuarial packages, there are more than just Julia actuary packages. I'm going to highlight the Julia actuary packages because I think it's, from my experience as a life and annuity actuary, most relevant to those folks. There are packages related to like mortality experience in other countries. This is kind of US focused because there's integration with like SOA tables. There's survival packages. There's like copula packages, which are not necessarily within like the scope of the Julia Actuary family of libraries. But the Julia Actuary family of libraries are ones I'd probably recommend first to colleagues, and are also ones that I've had a hand in authoring. So the first is representing mortality tables. So there's a mortality table library where you can pull in any table that's in the SOA's mortality table database, and there's associated functions like calculating survivorship or lives remaining. There's parametric functions like the Macomb-Gumpertz type of mortality models. There's a couple dozen different parametric mortality models. We can model like the hazard rates and things like that. This was actually probably one of the first major sets of functionality I wrote several years ago, because I found it so painful just to try and every time we needed to model something to just try and get the loading of the mortality tables correct. And so this kind of abstracts all of that headache of trying to map the right ages and durations, etc. There was a competing Python implementation, but I think I've kind of spoken with the author of that in a number of different times, and I think he basically says like the Julia implementation is definitely the cleanest, most performing implementation of mortality tables that are out there. LifeContingencies is a package that would, for example, utilize those mortality tables. And within LifeContingencies, there's different single and joint contingencies, and you can calculate different things like net premium, reserves at different points in time, what are the associated like unit cash flows or unit decrements, or a lot of different kind of basic actuarial maths available in that library. ActuaryUtilities implements kind of non-life contingency financial mathematics, so things like present value or duration or convexity. It also implements like risk measures like value at risk or tail value at risk or conditional tail expectation. But something I want to point out is what's really cool about this is a couple of things. One is present value is using a very fast present value function where this is, I'd claim that this is the fastest library to calculate the present value of a stream of cash flows of any language out there. But to calculate the duration, if you go in and inspect the source code, the duration calculated here, it's literally just using the derivative of the present value. It's not doing anything fancy. There's not like the entire like duration, the effective duration is calculated in just a few lines of code, because it's so easy to extend Julia in that way, where you define present value, you focus on the performance and the accuracy, and then duration is the first derivative of price, and it comes almost for free with the flexibility and extensibility of Julia packages. Of course, you don't always want the effective duration. Sometimes you want different definitions of duration, and so an alternate example of that is the Macaulay duration. And so this is like an example of multiple dispatch. So it's the same function, but because it has this Macaulay argument, it knows that it's going to use the Macaulay definition of duration. Similarly, convexity is the derivative of duration. So there's not a long chain of like nested finite differences to calculate convexity. It's just the derivative of the derivative. And it's really kind of easy as that. This example uses the FinanceModels library from Julia Actuary. A couple things going on here. First, note that the rates are defined as continuous rates. That's one of the things I'm pretty proud of in this library, is the ability for the code itself to distinguish between different rate quoting convention, whether it's continuous, annual effective, bond equivalent yield, or other. By telling the computer what the rates are and what kind of rates they are, it will appropriately change like the algorithm or the function that it uses. So it reduces the risk of like handing off, like this is from one part of the like program to another, this is a rate of like 1%. Well, is it 1% compounded continuously or 1% compounded like bond equivalent yield? And functions that are related to financial math implement the appropriate code because they can distinguish between the types of rates. The second thing that's going on here is that we're combining the rates with the maturities to define a set of contracts that are zero coupon bond yield. They're actually defining a set of fixed income contracts which have an associated price implied by the yields, and we use those quotes on those contracts to fit different yield curve methodologies. So you can see some of the available like yield curve functions or splines or like Nelson-Siegel or Siegel-Svensson or Smith-Wilson, and each one of those is fitting the same set of rates in a different way, and you can see that in the plot of what those different curves look like. Those curves themselves, so this, for example, this Nelson-Siegel fitted yield curve could be used in functions like, on the prior slide, the present value or the duration. So we're able to use an entire term structure of rates in the same function that we've defined here, present value or duration or convexity. I'm not aware of other publicly available libraries that let you do something like that. There's a lot of really rich functionality in FinanceModels, and it's designed to be very extensible so that you can define new types of yield curves or other types of financial like term structure, like FX or volatility surfaces, things like that. Definitely encourage you to check out the documentation to see just how extensible and powerful this library is. Another package which I would describe as more, I'd say it's beyond the proof of concept stage, but it's more of a technical preview, is EconomicScenarioGenerators. But I wanted to showcase it because, again, it's another way of like demonstrating how you can compose like two packages that don't know about each other, copulas and EconomicScenarioGenerators, and come up with a correlated economic scenario generator in very few lines of code, and it's very performant as well. Additional resources include like juliaactuary.org. There's a lot of examples and demonstrations available there. There's utilities for experience studies in a package called Experience Analysis, which is really because it's mostly focused on calculating exposures correctly. Because once you have the exposures, it's often just very straightforward to combine that with like data frames and calculate experience analysis. So it's not a fully featured experience analysis library. It gives you the components of like the logic that is unique to experience analysis, and then lets you use the fully featured like data frames or visualization libraries without needing to recreate it all within like one specialized package. There's a lot more library features that weren't shown in the prior examples. So I do believe that coding skills are going to be a prerequisite for an effective actuary in the very near future. I think that coding is a skill similar to math, similar to business knowledge, similar to like actuarial maths. And it's simply a tool. Like coding in and of itself doesn't make you a good actuary, but coding will let you implement a lot of the things that you do as an actuary much more effectively than other tools. And I think it will be, for the foreseeable future, the best way to do that. And in my view, not going to be displaced by large language models, and it's not going to be displaced by low code. I'd compare like low code solutions to trying to implement like mathematics with a limited set of expressions. Like why limit yourself arbitrarily? Because if you can express what you're trying to do in words, there are tools out there to help you write the code for that. And large language models are actually kind of a bridge in that way. They're not going to like tell you what should be done or like what the architecture of the model that you're trying to design. But if you're just trying to say, I want to iterate over this set of values, discount them, and sum them up, like if you can say that out loud, like yes, you could probably find a low code solution that does that. But once you can say that, you basically know the shape of the algorithm, and you just need to know the syntax of the language to implement it. Which is, syntax of the language is one of kind of a first step to learning a language, so it doesn't take very long to get there. I do think that one thing I would point out is I think there can be a distinction between business users who code. Business users who code don't need to know how to deploy like new servers and set up like all the infrastructure. I think there is still a role for what tech companies call DevOps. I might call it business ops, where you have like people supporting the technical business users, and the business users are focused on the like problem at hand. And then I think open source development is also really bullish on that for actuarial science. I think that there's really strong support across different companies. A lot of it is kind of a younger generation. I think there's a lot of people who, in my experience, we're hiring who say that I would prefer to work in code than to work in a spreadsheet. And I think it portends kind of the direction of our industry where people are getting more comfortable with code, and code basically relies on so much open source. I think there's going to be a lot more interaction with actuaries and open source. The Casualty Society is actually pretty proactive in this way and have their own GitHub organization with a number of existing open source casualty packages. More specific to this talk, I think there's a lot of support from the Julia community. So there are a handful of us actuaries writing Julia, but there's also just very smart, very engaging, and very helpful people across the different ways to connect with the Julia community, whether it's forum or Slack or Zulip or other places you connect with people online. I already talked about how there's a growing number of actuaries who code, but I think that will just continue to grow. And again, as a result, there's going to be an increase in acceptance of open source in companies and active development of new tools and package, both in kind of the open and open source and inner source, where companies are doing that internally.